Good morning, everyone. I am MD Rahan Kabir Khan from the Department of Electrical and Computer Engineering, North-South University, Bangladesh. Today, on behalf of my team, I will present our paper titled Simulation and Security Analysis of the BB84 Quantum Key Distribution Protocol under Intercept, Recent, and PNS attacks. This work focuses on analyzing the security behavior of BB84 in a dual receiver setting using simulation-based evaluation in Qiskit's basic simulator. Classical cryptographic systems such as RSA, DSA, and ECC, which is elliptic curve cryptography, are fundamentally threatened by quantum algorithms, most notably Shor's algorithm and Grover's algorithm. Studies suggest that roughly 4,000 logical qubits could break a 2048-bit RSA key within hours. Quantum key distribution, or QKD in short, offers a fundamental different approach. Instead of relying on computational hardness, it relies on quantum mechanics principles. The BB84 protocol, one of the earliest QKD protocols, uses quantum superposition, which guarantees that any measurement in the wrong basis disturbs the quantum state. That means if someone in the middle tries to measure on the wrong basis, the participants, which is sender and receiver, will be alerted. Even today, BB84 remains highly relevant, not only for secure key exchange, but also as a decoy state mechanism in multipartite QKD protocols. Despite extensive research on BB84, most studies focus on a single sender and a single receiver. There is a notable lack of simulation-based analysis that evaluates BB84 security in multi-receiver environments, particularly under intercept recent attacks and photon number splitting attacks. To address this gap, our objectives were to implement BB84 in a dual receiver framework using Qiskit basic simulator to analyze QBER shifted key length and IPS information using the simulator, and to compare the security impact of intercept recent and PNS attacks. Our simulations were conducted using Qiskit basic simulator. Key features of the methodology include over 500 qubits per simulation run, random basis selection using X and Z bases, a dual receiver configuration where Alice sends identical quantum states, quantum states to Bob1 and Bob2. We studied two attack scenarios: intercept recent assuming ideal single photon transmission, and PNS attack using weak coherent pulses with detector imperfections modeled via error probability. This allowed us to analyze both detectable and stealthy attack behavior. In our dual receiver model, Alice transmits quantum states simultaneously to Bob1 and Bob2 through a quantum channel where she measured transmitted bits in random measurement bases, which are X basis and computational basis, who also known as the Z basis. Before transmitted, each receiver chooses measurement bases independently from their side. That means if Alice measures one transmitted bit in Z basis and Bob measures in X basis measurement, Bob will get an unexpected result. To avoid this, both the receivers Bob1 and Bob2 will notify Alice what measurement basis they used for transmitted sequence, and Alice will do the same, and they will calculate QBER later. This setup models practical QKD networks and allows us to study scalability and consistency under identical attack conditions. The question is, how will they detect eavesdropping? Suppose if both sender and one of the receivers, maybe two, measures the same basis measurement, but the received result is still unexpected. It can happen for two reasons. One is the channel is noisy. In that case, they will just ignore the bit while generating key based on shifted bits. But what if it's too noisy? Theoretically, the QBER rate is supposed to be around 25% if any intruder is eavesdropping. Using Qiskit's basic simulator, we generate the intercept descent attack model where attacker tries to intercept the bit, measures it, then resend the bit. As they are not aware which basis our participants are using, this attack generates lots of noise in the quantum channel. Without any eavesdropping, Bob1 obtained in our experiment simulation, Bob1 obtained a 2239-bit key and Bob2 obtained a 267-bit key when there is no eavesdropping, and the QBER was 0 because there is no eavesdropping. When an intercept attack was introduced, QBER spiked to approximately 24 to 25%, which is around 25% of what I mean. If similarity to the key reached around 75%. This aligns closely with theoretical BB84 predictions. The key takeaway is that intercept resend attack introduced large, easily detectable disturbances, ensuring the protocol's security. Theoretically, in many papers on the BB84 QKD protocol has shown its resiliency against major attacks like intercept resend and ancillary attack. Even simply quantum simulations prove these claims. However, most of these ignore the imperfection of the quantum systems. Thus, PNS attack is introduced. Almost all the present quantum photon transmission systems don't use a true single photon source, as it's quite complicated to generate. They mostly depend on multiphoton weak pulses. Eve takes advantage of multiphoton pulses. She keeps one of the pulses of the photon and lets the rest of them to go to Bob without causing any noticeable error. This attack was made possible to show through Qiskit simulator because we introduced weak photon source and p error rate. Thus, the PNX attack produced a very different outcome. Here, QBER remained very low between 1 and 2.5%. Shifted key was significantly reduced due to the error and the noise introduced. Eve achieved the 100% information on multiphoton pulses. This demonstrates that PNS attacks are stealthy. They do not raise QBER enough to trigger alarm, making them particularly dangerous when weak coherent sources are used. This highlights a critical vulnerability in practical BB84 implementation. To summarize the comparison, in intercept resend attacks, it causes high QBER and it is easily detectable. However, PNS attack maintains low QBER and leak complete information silently, according to our simulation. Our dual receiver analysis confirms that while BB84 is robust against active disturbance-based attacks, it remains vulnerable to attacks like PNS. In conclusion, BB84 highly robust against intercept resend attacks. On the other hand, PNS attack can silently compromise security, and that makes us realize the importance of true single photon source. Dual receiver simulations confirm BB84's relevance in multiparty QKD research, and Qiskit proves to be an effective tool for realistic QKD security evaluation. Thank you very much for your attention. I will be happy to take any question.